So today I'll continue on stable rationality. Let me do a quick recap to make sure that we are all on the same page. Last time we introduced this the ring of stable birational types, which is sort of the simplest way to work with birational geometry or stable birational geometry. So it's really just the free abelian group on the set of stable birational types. So elements of this ring are just sort of formal integer coefficient linear combinations of stable birational types. And there was this very useful motivic volume formula proved by Nicaise and Shinder, which is basically defined by this. If you take, so this is in characteristic 0, if you take a scheme which is defined over this evaluation ring here, we assume that the generic fiber is smooth and that this is strictly toroidal. Then this ring map is a map from the stable birational types over well, on the generic fiber here to the special fiber. So you take the alternating sum of the strata of the special fiber. And one sort of very basic observation is that the volume maps spec big K to spec C. Like you could take the sort of the trivial family over R. But this is actually a very useful observation because it provides an obstruction to being stably rational. So the main point, and maybe this is sort of a slogan for the whole lecture series, like if you have a variety that you want to prove is irrational, the recipe is you try to write down a degeneration so that it breaks up into some smaller pieces. And then you try to look at this formula here and then try to sort of make sure that the terms do not cancel out to the class of a point. If you're able to do that, then the generic fiber could not have the class, I mean, the class of the generic fiber could not be the spec of a point, which means that it's not stably irrational. So it's a very basic observation. But it turns out to be very useful because in many cases you do have access to many degenerations like this. So that's sort of I mean, once we have this as a tool, the rest of the game is really to try to write down explicit degenerations and utilize this simple idea. Okay. Before we begin with the sort of main topic of today, let's just sort of see again one basic example of how this technique is used. So at the beginning, I mentioned that there are some results also for complete intersections, not just for hypersurfaces. So let's try to prove this. A very general intersection of a quadric and a quartic, so that's degree 2 and degree 4 in P8. So this is a sixfold. Is not stably rational. So again, this is one new case which was unknown before. And now we can sort of use this basic technique to prove this result. And the idea is to just write down degeneration of a family of complete intersections that degenerate into something where we can sort of compute this motivic volume. And the degeneration in this case is not very complicated. It's given by this formula here. So Q is some quadric. No, let's see. This looks right. Q is some quadric, and F is a quartic. So note that when t is equal to 0, you get something which is reducible. It's just, this quadric degenerates into two linear spaces. Okay, so you get two components. One is just f equal to f0 is 0, and f is x8 equal to 0. So we don't really know if these are stably irrational or not. I mean, these are quartic, six-folds. Yeah, so this is not covered by our previous results. But the point is that we don't really need to know whether these are stably birational or stably irrational. The point is that we do know that their intersection, that would be when both of x7 and x8 are 0. That's a quartic fivefold. And that is covered by the result that we had last time. So if we take that as sort of an input to this sort of basic idea, then, well, what we do know is that we have something where we don't know. Maybe they're both rational, but it doesn't matter so much. What we end up with is this alternating sum. And there's sort of two cases that could happen. Like either they're both rational, or both stably irrational, but this we know is stably irrational. So if these are both spec C, this couldn't cancel out to be spec C. And it could be that both of them are irrational, so that all the three terms here are also irrational, but still that couldn't cancel out to spec C, because this is the free abelian group on stable birational types. So if this is stably irrational, it could only cancel out with one of them. Yeah, so in any event, we get that this alternating sum is not equal to spec C. And here it's the point that you can choose both of these to be very general quartic six-folds. Otherwise, it doesn't work. Okay, so it's not a very complicated proof, this, but it sort of generates lots of new results on irrationality of complete intersections. Okay, so here's sort of one other result. Maybe I won't go through all the details. It's just saying that if you have some bounds like this, then the general complete intersection of quadrics is stably irrational. So if you take a hypersurface, there's sort of various things you could try to do when you try to degenerate. If you take a complete intersection of quadrics, that's sort of it's less obvious what to do with that. But what you can do is just to take one of the quadrics and degenerate to, again, a union of linear spaces. I mean, it's the most basic thing that you could do. You can take a quadric and degenerate it into two linear spaces, and the intersection will be another complete intersection of quadrics. And by induction, we get this result here. So you just need one base case, or a few base cases, and that generates sort of infinitely many new results. Of course, you might not be impressed by this particular argument, but I mean, these are sort of classical objects in birational geometry. So it's sort of incredible how easy you get these results here. So I do still quite like it. Anyway, the point of these examples is that, well, you do get some new results, but it really requires very stupid degenerations, like taking a quadric and breaking it up into two linear pieces. That's the least sophisticated thing that you can do. So the point of today is to develop a more sophisticated way of writing down degenerations, and they will use toric degenerations. And the idea is that if you have a toric variety, you can sort of degenerate this using combinatorial techniques, and then you typically get more components. And then the idea is that if you have many components, then you get strata of very small dimension, and then that's good for our purposes. Okay, so I do not assume that you're sort of familiar with the whole toric degeneration framework here, so I'll just try to cover what I would need for that. I think I do assume that you're familiar with toric varieties, so that there's this correspondence between projective toric varieties, which are polarized by some ample line model, and polytopes. So every lattice polytope gives you a toric variety just by taking the normal fan of the polytope. So this particular example is the first Hitzebruch surface. So it's the blow-up of P2 at a point. But the main point is that there's a correspondence between the toric strata, so like this one, and the subvarieties, or the torus invariant subvarieties of the toric variety. So this red facet here corresponds to some, the exceptional curve in the blow-up. Okay, so the most concrete way you can define this is to just take if you have a lattice polytope, you take the lattice points, and then you define the map from the torus into the projective space just by taking the monomials corresponding to these lattice points, and then letting x be the closure of this image. So this is, if you haven't seen toric varieties, this is sort of the simplest way to think about it. Okay, so it's clear that you get a predictive variety in this way, and it's a very convenient thing that you can sort of generate varieties in this way from lattice polytopes. Okay, so as I said, there's a convenient bijection between the faces of the polytope and the toric strata of the toric variety. And one should really think of this as a sort of a pair. It's like x plus some ample line model. So it's defined as the proj of a ring, so it has a line model coming from it. And the point of this is that the global sections of this line model corresponds to the lattice polytopes. Okay, so here's a sort of basic example. Projective space. This corresponds to the usual n-dimensional simplex. And if you scale the simplex, you get to you still get the same polytope. It's just scaled so that you just basically take the divisor and multiply it with d. So this corresponds to the Veronese embedding. Okay. So this picture here is the sort of, it's 4 times the unit simplex. So you should think of this as sort of corresponding to quartic surfaces. So it's P3 polarized by O of 4. Okay, I think I'll skip this slide here. If you consider this trapezoid polytope, this corresponds to the blow-up of the P2 at a point. Okay, so now maybe let's move on to something a little bit more useful for our purposes. So these are regular subdivisions. These have already appeared in some of the talks already, but let me just explain what I mean by this. So basically, if you have a polytope, you can define a subdivision using by taking some piecewise linear function and then projecting. You take the graph polytope. This is what I mean by the graph polytope. You take the graph, and then you take everything that's above the graph, and then you project the faces of this down to subpolytopes of delta. So if you choose some linear function or a piecewise linear function, so that this is convex or strictly convex, you can project the faces down here, and you get a subdivision of the polytope. Yeah. So these are special subdivisions of polytopes that have this associated function to it. And the point is that once you have this, you can write down a corresponding toric degeneration. So if we have a polytope, we can construct a degeneration from, well, x over a1, so that if you take the generic fiber, or I mean, you remove the special fiber, it's just a trivial family, so it's really just the polytope, the toric variety that you started with.
Excuse me, I have just a question. What means strictly convex here? Because there's some parts where it's not strictly convex, because it's linear.
Because it's what?
It's linear. The feature.
Strictly convex means that if you have a face and you take a hyperplane which is tangent to that, then it really cuts the polytope in exactly that face. Yeah. Okay, so yeah, the special fiber of the degeneration breaks up into a union of toric varieties. And the point is that the special fiber is also a union of toric varieties, and it's the toric varieties of the polytopes that appear in the subdivision. Okay, so you have some polytope, you find this subdivision, and there's a corresponding degeneration, so that the toric variety breaks up into pieces, and the pieces correspond to smaller toric varieties, where the polytopes appear in the subdivision here. And the nice thing is that you know, we know how these intersect in the special fiber. I mean, if you have two polytopes in this special fiber, no, sorry, in the subdivision, and they share a common face R, then the two strata intersect along, you know, the corresponding subvariety. So the way that these polytopes intersect in the subdivision sort of reflects how the strata intersect in the degeneration. Okay. Yeah. Yeah. This is just how you would define that. Basically, this function that we have, this lambda tells you how to act by multiplying with t. And one way to define this degeneration is just by sort of taking the graph of this C star action on the toric variety. So you can actually just write down in formulas what this degeneration does. Okay. So yeah, you should think of this lambda here as just, yeah, the way that you scale by a C star action. Okay. Yeah, let me not go through this. This is just a proof of this fact that I mentioned, that the strata really corresponds to the polytopes in the subdivision, and it sort of checks that they intersect the way I said. Yeah. So maybe I'll just skip this actually. I think it's clear to just do an example. If you take P1 cross P1, yeah, this is the polytope of P1 cross P1. And if we subdivide by adding the diagonal here, well, one way to do that is just by taking the function which is 0 here, 0 there, 1 there, and 1 there, so that it's sort of a, yeah, you sort of fold the square. This represents the degeneration of a quadric surface into two P2s. And they intersect along the toric variety with this as the corresponding polytope. So that's P1. Okay, and yeah, here's how you would actually compute this degeneration. You would let t act by these weights. So you put 0 here, 1 here, 0 there, and 1 there. So 0 there, 1 there, 0 there, and 1 there. And if you take the Zariski closure of everything here, the degeneration is given by this. Okay. This whole thing is just because we want a recipe to degenerate or to write down concrete degenerations. This is very standard stuff from tropical geometry. Yeah. So another sort of convenient way of writing this down is to use a Newton subdivision. So if we have a polynomial with the coefficients in this Puiseux series field here, then you get for free this sort of piecewise linear function just by taking the t-adic valuation of the coefficients. So for instance, if we take this polynomial here, you see that there are coefficients in t, and this represents the degeneration we just had. Yeah, so it's just, you have 1 here, and sorry, the degrees of the t's are 0 here and 0 there, so that corresponds to sort of the diagonal. Okay, so we know how to degenerate toric varieties. Okay, just maybe one more example. This is how you would degenerate a cubic curve in P2 into a union of, two toric surfaces. This is the polytope of P2, and this is the polytope of the blow-up of P2. And you can do it by writing down this polytope here. No, sorry, this polynomial here. Okay, so of course we don't really want to just degenerate toric varieties. We're really interested in hypersurfaces inside toric varieties. Those are the ones that we want to prove are irrational. But the thing is that if you have a toric variety and a hypersurface in that, and you degenerate the toric variety, you get for free a degeneration of the hypersurface just by taking the Zariski closure. So if we start with some polynomial, and we assume that all of these, you can define, so if we have a subpolytope in our subdivision, if we just assume that that these hypersurfaces here are smooth for every polytope in our subdivision, the degeneration that we're going to get will be quite nice. So yeah, if we base change to our discrete valuation ring, we get a degeneration over, we get a family over spec R, and a corresponding degeneration of the hypersurface F over A1. Oh, sorry, this should be spec R, I'm sorry. Yeah. Yeah, so this here is just, now we have a family of degeneration, we have a degeneration of hypersurfaces inside the toric variety. Yeah. So yeah, it's really nothing more than that. We know how to degenerate toric varieties, and if we take a hypersurface in the special fiber, we can just sort of take the Zariski closure in the special fiber. But we use this non-degeneracy condition, which is important. Okay. So let's define a lattice polytope to be stably irrational. If you take a polynomial, like a very general polynomial with that Newton polytope, and that hypersurface is stably irrational, well, yeah, then you say that the polytope is stably irrational. Otherwise, we say that delta is stably irrational. So, yeah. So, stably irrational polytopes just means that, if you take a very general polynomial with that Newton polytope, that's really stably irrational. So, for instance, if you look at the scaled simplex, this is stably irrational if and only if the generic hypersurface in Pn n plus 1 is not stably rational. Yeah, so of course this is a condition that we're interested in. We're interested in sort of which polytopes are stably irrational. Okay, so here's one interesting stably irrational polytope. So it's this product polytope. You take 2 times the polytope of P2 and 2 times the polytope of P3. Okay, the product would be the polytope of P2 cross P3. And Hasse-Pirotka-Chinkel proved that that's a stably irrational polytope. I mean, what they proved is that this equation here gives you something which is stably irrational. So here's a very concrete 2-2 divisor which is stably irrational. But the fact that this is stably irrational means that sort of all of the, or the general 2-2 divisor is stably irrational. So this is a stably irrational polytope. Sorry, EQ? Yeah, the cube, I tried to draw a product polytope. Yeah. I don't know, yeah. Okay. But yeah, this is a very useful equation actually, because it's concrete. It means that we have something that's very concrete that we can try to degenerate to. And we know that this is stably irrational. So if you can find this as one of the strata somewhere, we're very happy because it's stably irrational. Okay, so those were stably irrational, but what about rational polytopes? So here's a very simple, useful lemma. If you have a polytope with lattice width 1, so lattice width, that means that I have a polytope and I can find a linear change of variables so that it's really just contained in like hyperplane and then translate by a hyperplane. So it's, yeah, it means that the width is really 1. You have a hyperplane here, hyperplane there with distance 1, and you can fit the polytope between these 2 hyperplanes. So if you have a small polytope like that, then it's stably rational. And this is a very basic observation, but it's because the equation really is linear in one of the variables. If you take a hypersurface which is linear in one variable, you can just solve the equation. So it's not an irrational polytope, or it's not an irrational hypersurface. So for instance, we could take this polynomial here. We look at the 0 set of that polynomial. That's not going to give an irrational curve, because you have, if you project to the y-axis, it's going to be generically 1-to-1. I mean, it's a linear equation in y. So this is a nodal cubic, so it is rational. Yeah, and here you really see that it has lattice with 1, this polytope here. So this is a very basic class of polytopes which do correspond to rational hypersurfaces. So the intuition is that if you degenerate and you have lots of smaller polytopes, those small polytopes will correspond to rational hypersurfaces because of this. Okay. So here's a general strategy. Well, we take a subdivision of our polytope. So we're really interested in some toric variety and some hypersurface in the toric variety. And then we try to find some subdivision of the polytope so that all but one lower dimensional polytope is stably rational. So that means that, okay, another attempt to draw a big polytope here, but you have some toric variety that you care about, and you want to try to find a subdivision so that somewhere inside the corresponding strata there's something that's irrational, like this. And ideally, you would have just that one irrational thing and the rest rational. So if you can do that, then this alternating sum in the volume formula will not be able to cancel out to spec C, because you have this irrational guy, it just never goes away, and you have lots of rational things, that this alternating sum could just never be this class of a point. So that's the strategy for doing this. And yeah, in the rest of the lecture, I'll just show that this sort of naive strategy is quite successful.
Then you have to have one irrational polytope and you have
No, it's just enough in some dimension, yeah.
because then you take the product of that with something irrational.
No, I think, no, let's see. So maybe I can try to clarify this point. So we take, so the volume of this degeneration would be something like this. Yeah. So if you know that, say, there's just like, so E is the set of strata here. Yeah, so E is one of the strata. So if there's only one that's irrational, exactly one, then this whole thing is like plus minus irrational plus something, which is the class of a point. And the thing is that this will not be the class of a point. So that's the most naive thing that you can do. Another thing you could try to do, you know, if two irrational guides showed up, you could try to make sure that they're not birational to each other. But if you're lucky, this happens. And the thing is that it would be sort of unlucky that you have two irrational. Because if you do that, maybe you could just subdivide even further so that everything, yeah, I mean, maybe just get one and then the rest irrational. So that's sort of the naive thing, that we're looking for subdivisions like this so that there's exactly one irrational that shows up. Okay, so let's see how this works. Yeah, okay. Before we go to the sort of main applications, here's the sort of follow-up to the sort of funny example that we had. So remember that we had this sort of funny argument that if the quartic threefold is irrational, then one of the two cases, like either the quintic fourfold is irrational or the quartic fourfold. We didn't know which one, but there was this funny argument. But here we can sort of improve this statement. So suppose that we know that a very general hypersurface of degree d in Pn plus 1 is stably irrational. So the n-dimensional hypersurface of degree d is stably irrational. This is the input. Then, if you increase both if you increase the degree, then this is also stably irrational. So if you know that a degree 4 hypersurface is irrational, then all of the higher degrees will also be. I mean, this is maybe not so surprising, but because you're increasing the dimension, but it's not obvious that these rationality problems are related to each other. And you can also, let's see. I think there's something odd about this should be irrational for sure, yes. That's only one problem with this statement, I think. It should be that you can increase the degree by 1 and also the dimension by 1. I don't think you can deduce, yeah, so, okay. I think it should be d plus 1 and n plus 2. Okay, so you can if you can increase both the dimension and the degree, you get a new result. Okay, anyway, this is what I'm going to explain. Yeah, for instance, if you have quartic fivefolds, which we do have, we get quintic sixfolds, sextic sevenfolds, and so on. So we can always increase the dimension if you also increase the degree. And the proof is basically just a picture. Here's the, so if you take the following hypersurface, this is the, sorry, this, yeah, so this would be sort of increasing the degree and also the dimension. If you subdivide like this, then we win. So this is the, I mean, it's supposed to be a simplex, this. And this is supposed to be a simplex of 1 dimension lower and 1 degree lower. So you can always, I mean, if this is the, if you have the n plus 1 simplex, you can always fit, yeah, a smaller simplex in like this. And then we can subdivide the rest of the smaller polytopes like this. So the point is that there's some sort of induction that happens here. So the input is that we know that this is irrational. That's why it's red. And we want to conclude that the whole thing is irrational. But here's the proof why everything else is rational. It's just because all of these other polytopes have lattice width 1. Right? And this is, you know, this is sort of expected. Like if you force this irrational polytope into this bigger polytope, and you just subdivide like randomly, you expect that these other pieces will be small or have some lattice width 1. So yeah, here, the red polytope corresponds to a degree d hypersurface in Pn, so that we sort of assume is irrational. And all of the other polytopes have lattice width 1, so they are rational. And therefore, by this formula here, we get something which is irrational and something which is rational.
So and you have to show that the faces of this polytope are irrational.
Yeah. That they're rational?
They should be rational because you want to have a unique polytope in yourself. The big one should be rational. So in this dimension, it is okay, but in higher dimension, you have to assume that the faces of this red polytope are also rational.
No, I think because the faces, they're in the boundary of the big polytope, so they wouldn't, I mean, it's only the interior face that would correspond to the, yeah.
I'm sorry, I don't understand the picture. So, what is the subdivision?
What is the?
What is drawn is not the latest subdivision, right?
Yeah, maybe this is, I mean, maybe it would be, wait, why is it? Why is it not a regular subdivision?
Oh, it's not a subdivision at all, because for a subdivision, the intersection is a common face.
Oh yeah, okay. Yeah, sorry, maybe the figure is wrong. Yeah, let's see. Yeah, maybe, yeah, my figure is not great, yeah. Yeah. Yeah, so maybe add this edge here. Yeah, you're right, definitely, yeah. Okay, the point is that if you just sort of shift the polytope one step like this, you get a simplex, which, I mean, you get another simplex, and you just take any, like, subdivision with where the polytopes have lattice with 1. Yeah. Okay, so that's yeah, it's the figure that's wrong, not the argument, I think. Okay. Yeah. Any other questions? Or, yeah. Okay. Yeah, let's go back to the quartic fivefold. So the quartic fivefold corresponds to this polytope. It's 4 times the simplex in R6. So here, yeah, it's another picture, but yeah, you can subdivide the simplex like this, so that there's one polytope that corresponds to a product polytope. So this is like 2 times 2 polytope. And then you can just subdivide the rest by sort of adding hyperplanes, so that it looks like this. So this is a regular subdivision. Yeah, and this we know is the polytope of something irrational. So this is exactly this Hasse-Puruka-Chinkel example that we had. We had P2 cross P2, 3, and a 2-2 divisor. So we know that something here is irrational. So that's the red polytope that you see here. Yeah. But if you look in this picture, well, if you look in the 6-dimensional analog of this picture, that you can just see that all of the other lattice polytopes have lattice with 1. So all of the other polytopes are rational. So there's this one irrational guy, and then all of the other polytopes have lattice with 1. And in any case, what we get is something irrational, and then something which is rational, some pieces. And this simple argument here shows that the quartic fivefold is irrational. So this is a different proof than what we had, because in the previous lecture we degenerated the quartic fivefold into 2 components. So there it was sort of, we got this situation where we had these 2 pieces, and then we didn't know whether these were irrational or not, but we knew something about their intersection. But here we don't really need that. We get this one polytope which we do know is irrational, and the rest we know is rational. So that's even cleaner, I think. But if you want, this is it's possible to realize the previous degeneration by this picture. Yeah. All right. So here's another result, another theorem. If you look at a very general 2-3 divisor in P1 cross P4, this is also not stably rational. So the point is that most of the rationality techniques, they're very well suited for product. I mean, the classical techniques are very well suited for Fano varieties of Picard number 1, or they're in projective spaces. But of course, our methods really apply to any toric variety, in particular P1 cross P4. And there, the sort of classical results do not work so well. Like birational rigidity, for instance, it doesn't really know how to solve this case. But here we can just take this the polytope 2-3, and then we could try to subdivide again. Oh yeah, and by the way, this 2, 3 is basically the best you can do. Like if you take 2, 2, or like something else which is smaller, then it's rational. So this is really the optimal one. And just like, so if we know that AB is stably irrational, then you can increase the degree, the by degree in both directions. So if you prove that 2, 3 are irrational, you get all. So this is really the main case. Yeah. Okay, so the point is to use again this Hasse-Piruka-Chinkel quartic, which we do know is stably irrational. And the nice thing about this is that it has a very small Newton polytope. There are very few monomials, and it's not like a generic quartic polynomial. So again, we know that this polynomial here, it corresponds to something which is stably irrational, and this is what we are going to use as input in our argument. So if we let P be the Newton polytope of this irrational equation, well, this is what it is. It's the columns of that matrix here. Then the nice thing is that we can embed that polytope as a sort of smaller polytope inside the general 2-3 product polytope. So this is the 2-3 polytope. So that would correspond to P1 cross P4 and hypersurfaces of degree 2-3. So now the point is that this corresponds to a fourfold, this is also a fourfold, and we just notice that this polytope here lies inside here. So in geometric terms, it just means that you can sort of re-embed this the Hasse-Piruka-Chinkel quartic as a 2-3 divisor. Okay, but now we can just sort of find some nice subdivision. So basically, the most naive thing that you can do, you have a big polytope, you have something like you have a smaller polytope inside it. You just take the function that's the sort of distance to the smaller polytope. So this is a convex function. And that defines a subdivision. And what we get is a bunch of toric varieties. So we have 26 polytopes in this subdivision. And one just checks that, well, by sort of construction, our smaller polytope lies inside here, somewhere in the strata. And we just check that the other polytopes that we end up with, they're all lattice width 1. So it's something, I certainly didn't go through all of these polytopes, but it's something a computer can do very quickly. You just check whether a polytope has lattice width 1. It's a for loop, and then you sort of algorithmically prove that these hypersurfaces are irrational. Oh yeah, okay, so in any case, we get something which is irrational, and then the rest is irrational. Okay. Okay. For the very last example of this lecture series, I would like to talk about a result which does not, it's not about toric varieties. It's where the ambient variety is a Grossmannian. So the point is that this technique of using toric degeneration, it allows us to prove things about hypersurfaces in sort of other ambient spaces than projective space. So here's a theorem. It's about the Grossmannian G25. So if we consider hypersurfaces inside the Grossmannian, then this is stably irrational if the degree is at least 3. So you take the Grossmannian in P9, you intersect with some cubic, and this is an irrational Fano variety. And this is again optimal. If you take degree 2, this is rational. And the same thing for complete intersections. Like if you have 2 hypersurfaces, we know exactly when these, the exceptions when these are stably irrational. And the same thing with 3 hypersurfaces. So this is a final 5-fold, this is a final 4-fold, and this is a final 3-fold. Yeah, the point is that these are sort of famous Fano varieties. I mean, hypersurfaces are the most important class of Fano varieties from the rationality problem perspective. But this is sort of the next case where you place projective space by a Grassmannian. So in a particular case where you take a quadric and a linear space, you get these Grishel-Mukai varieties, which are much studied in birational geometry. Okay, so the point is that we have equations for the Grassmannian inside P9, but now we can just take a toric degeneration of the Grassmannian. You can just act on the P9 by a C-star action, and if you deform the Grassmannian, you can deform it to a toric variety. So the Grassmannian is defined by lots of Plucker quadrics. So if you act by C-star, this gives a deformation of the Grassmannian to something which is, in this case, a toric variety defined by this ideal. And one can check that this toric variety, it's very singular, but this is the sort of polytope that defines this toric 6-fold. So this is a toric 6-fold, which is a specialization of the Grassmannian. But then, what we want is to, prove that this polytope here contains lots of irrational subpolytopes. Like if you want to prove that a cubic intersected with the Grassmannian is irrational, you basically need to show that this is an irrational polytope. One has to worry a little bit about singularities in this example, but yeah, one just checks that. And again, we use this Hassett-Biruka-Chinkel example. So this is sort of the nicest polytope that we know that corresponds to stably irrational 4-folds. And in this case, we're able to take this polytope that we had before and embed it into our 6-dimensional polytope. And that's basically it. Once we have a big polytope and we found some irrational polytope inside it, it would be very unlucky if this technique didn't work. And we just check that the idea that we had before by taking this sort of distance function, this gives a subdivision which works. So the point is that this is basically it's an algorithm. Like you can take any variety, and you could you can take a toric degeneration of this, and now you can sort of continue using this subdivision thing. And basically, it's a way to prove that hypersurfaces in any ambient variety is stably irrational. So you first degenerate to a toric variety, and then you apply a toric subdivisions. So I do think this is a quite useful method. The whole point is that you can sort of deduce irrationality results in smaller dimensions to get irrationality results in higher dimensions. So I think there are more applications of this technique in the future. Okay, so I'll stop there. Thanks.
Thank you very much. Questions and comments, please?
Yep.
Do you know a good way to generalize toric degeneracy in the case of non-convex subdivisions?
No, no. I haven't thought about this. I'm not an expert in this area, so maybe other people have been working on this. Yeah, no, I don't. Yep.
Thank you. So I think your method shows that if you have a polytope and you can find a section of that polytope which
Yep.
is irrational,
Yep.
then the polytope itself is irrational.
Yes.
So do you think that there are finitely many irrational polytopes in each dimension, in the sense that any polytope which does not contain one of those polytopes as a section will be irrational?
I think if you take, I mean, you can have arbitrarily long polytopes with lattice with 1, I think.
Yeah, but those are rational. So this
Oh.
is the opposite. So
So finitely many irrational, or?
you want to finitely many irrational polytopes
Yeah.
which determine rationality in each dimension. In
Oh,
the
I see.
the sense of having a section.
I see.
I think the irrational polytopes form a semi group,
In this sense, yes.
and that semi group is finitely generated.
I don't have that much data to base this on, but I mean, that would be very nice if this was true. Yeah, I mean, usually we use this one polytope, always, this Hesse-Pruka-Chinkel, but I don't really know how to, I mean, for fivefolds we have some also results, but yeah, I don't have so much intuition in higher dimensions.
Are there any questions or comments? No? So, 5 minutes? So, for 5 minutes break? Okay. So we'll start at 10 past 10, so thank you.